This paper introduces a novel class of online learning algorithms, Generalized Implicit Follow-The-Regularized-Leader, FTRL, which expands the scope of the FTRL framework. By substituting the linearization of losses with a Fenchel-Young inequality, the framework enables the design of new update rules. Notably, it can recover known algorithms, including FTRL with linearized losses and implicit FTRL. The authors demonstrate the flexibility of the framework by showing that certain algorithms, such as Mirror-Prox updates, are instantiations of the generalized implicit FTRL. Moreover, the framework allows for the recovery of the temporal variation bound of implicit online mirror descent, OMD, with the same computational complexity. This highlights the potential of generalized implicit FTRL to unify and extend existing online learning algorithms. The generalized implicit follow-the-regularized-leader algorithm expands the FTRL framework by constructing update rules that minimize an upper bound on regret, thereby retaining the coupling between design and analysis. This approach offers a worst-case guarantee not to be worse than standard linearized updates. Notably, it recovers known update schemes and extends updates designed for online mirror descent to the FTRL case, showcasing the flexibility of the proposed framework. Importantly, the authors demonstrate that their approach achieves the same regret bounds as implicit OMD with the same computational complexity. This is a significant advancement, as it provides a constructive framework for implicit updates in FTRL, differing from previous work on implicit mirror descent in FTRL updates. By directly constructing the update rule, the generalized implicit FTRL algorithm effectively minimizes an upper bound on regret, thereby ensuring a robust performance. This novel approach has significant implications for the field, offering a unified framework for designing and analyzing online learning algorithms. The authors of this research paper introduce a novel generalized formulation of the implicit follow-the-regularized-leader (FTRL) algorithm, which diverges from traditional implicit or linearized updates. The main idea is to design updates that directly improve the upper bound on the regret, rather than relying on subgradients. The authors utilize the Fenchel-Young inequality to derive a more general strategy, which involves using the Fenchel conjugate of the loss function. The Fenchel conjugate of a function f is defined as f star operator, theta, equals sup x element of rho theta, x. F, x. Properties of Fenchel conjugates are provided, including the Fenchel-Young inequality, f, x, plus f star operator, theta, is greater than or equal to theta, x. Two theorems from Orabona, 2019, are also presented, which provide equivalent conditions for a function f to be proper, closed, and convex, and for a function psi to be strongly convex. The generalized implicit FTRL algorithm is presented, which involves minimizing the function ht, z, equals psi star operator t plus 1, v, theta tz, plus l star operator t, z, to determine the optimal setting of zt. The algorithm also involves two alternative updates, ht, z, and hd, z, which are used to guarantee a strict improvement in the worst-case regret. A regret guarantee for the algorithm is provided in Theorem 3.1. The theorem bounds the regret in terms of the regularizer psi and the surrogate linear losses. The bound involves the Fenchel conjugate of the regularizer and the loss function, as well as the optimal setting of zt. The authors highlight the advantages of the generalized implicit FTRL algorithm, including its ability to cover cases where zt is not a subgradient of the loss function. The algorithm is also shown to subsume traditional FTRL updates, and provides a more general strategy for online learning. The authors present a generalized implicit follow-the-regularized-leader (FTRL) algorithm, analyzed using a novel regret bound. The regret bound, denoted as regret t, u, is upperbounded by the sum of three terms: psi t plus 1, u, min x element of v psi 1, x, a term representing the algorithm's performance, and ft plus 1, xt plus 1, ft plus 1, u, which is related to the FTRL equality. The proof involves several key steps, including the FTRL equality from Orabona, 2019, Lemma 7.1, and the Fenchel-Young inequality. The authors then simplify the bound by adding and subtracting ht, gt, and h at gt, leading to the final regret bound. This bound is interesting as it recovers the linearized FTRL algorithm and provides a unifying way to design generalized implicit updates. The authors also compare the generalized implicit FTRL updates to implicit online mirror descent (OMD) updates, showing that they recover different variants of implicit updates. The Generalized Implicit Follow-The-Regularized-Leader (FTRL) algorithm extends the traditional FTRL algorithm, characterized by two implicit updates with shrinking effects towards the zero vector due to time-varying step sizes. The first update, given in equation 4, computes the subgradient of the loss function at the next point, while the second update, given in equation 5, computes the subgradient at the current point. Both updates are compared to the implicit online mirror descent (OMD) update, equivalent to the generalized FTRL updates with constant step sizes over time. The concept of temporal variability bound is introduced, quantifying the advantage of the generalized implicit FTRL updates in the case of slow temporal variability of the loss functions. Implicit OMD satisfies regret guarantees dependent on the temporal variability Vt, which can also be achieved by FTRL with full losses, albeit at a higher computational cost. The authors aim to demonstrate that the proposed algorithm 1 can achieve the same guarantee as implicit OMD with the same computational complexity. A key result, Lemma 4.1, provides a guarantee for the generalized FTRL algorithm under certain assumptions, including the convexity of function v, the strong convexity and subdifferentiability of the distance-generating function psi t, and the convexity and subdifferentiability of the loss function lieutenant. The lemma also requires the step sizes lambda t to satisfy lambda t plus 1 is greater than or equal to lambda t. Ultimately, the proposed algorithm 1 can satisfy the same guarantee as implicit OMD with the same computational complexity. The Generalized Implicit Follow-The-Regularized-Leader algorithm is a key contribution of this research paper. The algorithm is founded on the concept of regret bound, which is derived using the properties of the loss functions and the regularizer. Specifically, the proof involves leveraging the first-order optimality condition and the strong convexity of the regularizer to establish a bound on the regret. This bound is subsequently used to derive a corollary that depends on the temporal variation, providing a more nuanced understanding of the algorithm's performance. Notably, the paper also presents a simpler update rule, which utilizes an increasing regularizer that is behind by 2 steps. This approach, detailed in Corollary 4.3, enables a more straightforward update rule. The section further explores the concept of 2-step updates, proposing a simple approximation for the optimal ZT. This involves setting ZT as a subgradient after one fake update, an approach reminiscent of the Mirror-Prox algorithm. Theorem 5.1 demonstrates the effectiveness of this approach under certain conditions, highlighting the potential of the Generalized Implicit Follow-The-Regularized-Leader algorithm in addressing complex optimization problems. The Generalized Implicit Follow-The-Regularized-Leader (FTRL) algorithm satisfies the inequality $h_t, z_t, like h_t, g_t, where $h_t, z, equals psi_t, v, theta_tz, plus L_t, z, $. This inequality is crucial for bounding the worst-case regret of the algorithm. The proof relies on the strong convexity of $L_t$ and the smoothness of $psi_t$. By using the definition of smoothness and strong convexity, the authors bound the difference between $h_t, z_t, and $h_t, g_t, ultimately showing that $h_t, z_t, like h_t, g_t, $. The authors also generalize the aProx updates to arbitrary regularizers, demonstrating that they satisfy the inequality $h_t, z_t, like h_t, g_t, $. This implies that these updates are guaranteed to be at least as good as the subgradient $G_T$ in minimizing the worst-case regret. The authors define the truncated linear model $L_T$ around $X_T$ as $L_T X equals max L_T X_T plus Langle G_T XX_T wrangle $0 and extend the aProx updates to the case of generalized implicit FTRL. Theorem 6.1 states that under certain assumptions, the update rules for $Z_T satisfy the inequality $H_T, Z_T, lec H_T, G_T, $. The proof involves deriving inequalities on the quantities of interest, using the properties of the truncated linear lower bound and the definitions of $H_T and $H_T. The authors present the Generalized Implicit Follow-The-Regularized-Leader (FTRL) algorithm, which can be written in closed form when the regularizer is psi t x equals lambda t 2 parallel x parallel 2. The update rules for generalized implicit FTRL are derived, mirroring those of aProx. The performance of different choices of ZT in algorithm 1 is compared when psi t x equals lambda t 2 parallel x parallel 2. 4 variants of FTRL are considered: FTRL with linearized losses, implicit FTRL with aProx updates, implicit FTRL with two-step updates, and implicit FTRL with proximal updates. The authors adopt the choice of lambda t from Corollary 4.3. Experiments are conducted on linear prediction tasks using datasets from libSVM, with the hinge loss and logistic loss for classification, and absolute loss for regression. The datasets are normalized, and a constant bias term is added to the features. The authors plot the averaged loss versus different choices of hyperparameter beta, showcasing the algorithm's sensitivity to beta and their best achievable performance. The results show that FTRL with linearized updates is more sensitive to the setting of beta and performs worse than the other generalized implicit updates. In contrast, generalized implicit FTRL with two-step updates exhibits remarkable performance, making it a viable alternative to aProx. The confidence intervals for all implicit updates are very narrow, indicating robust performance. The authors demonstrate the robustness of generalized implicit follow-the-regularized-leader (FTRL) models by showcasing their performance in various tasks. Figure 2 illustrates the logistic loss, averaged loss versus the hyperparameter beta, highlighting the robustness of implicit FTRL updates, which outperform FTRL with linearized updates in terms of sensitivity to beta. The authors observe that implicit FTRL with two-step updates achieves the best performance, a conclusion reinforced by Figure 3, which displays the absolute loss, averaged loss versus the hyperparameter beta. The confidence intervals in the regression tasks lead to similar conclusions as in the classification tasks, underscoring the robustness of generalized implicit FTRL. The authors propose a new framework, generalized implicit FTRL, which not only recovers known algorithms, such as implicit FTRL and FTRL with linearized losses, but also provides a theoretical guideline for designing new algorithms, like extensions of aProx and Mirror-Prox. This unifying framework is general, flexible, and theoretically grounded, making it a significant contribution to the field. Future research directions include exploring this framework further by designing new algorithms with low computational complexity. The authors note that the two-step update seems to be a valid alternative to aProx updates, despite the additional computational expense of querying an extra gradient in each round. The Generalized Implicit Follow-The-Regularized-Leader (GIFTRL) algorithm is a novel approach to online learning, combining the strengths of Follow-The-Regularized-Leader (FTRL) and implicit online learning (IOL) algorithms. This adaptive method handles dynamic objective functions by leveraging two main components: a proximal term that encourages stability and a prediction term that promotes adaptivity. Through iterative updates using linearized approximations, GIFTRL achieves efficient computation and improved convergence rates. The algorithm's versatility is demonstrated through applications in linear regression, logistic regression, and support vector machines, showcasing its ability to accommodate various machine learning problems. Theoretical guarantees are provided, confirming that GIFTRL achieves sublinear regret under certain conditions. The paper provides a comprehensive overview of related work in online learning, including the development of FTRL and IOL, as well as other adaptive optimization techniques. It highlights the limitations of existing methods, emphasizing the need for a more flexible and adaptive approach, which GIFTRL addresses. Future directions are discussed, including the potential application of GIFTRL to non-convex optimization problems and the development of more efficient algorithms for specific domains. The work contributes to the advancement of online learning algorithms, offering a new tool for practitioners dealing with dynamic environments and changing objectives. I'm happy to help. However, I notice that there is no content provided for me to refine. Please provide the transcript of the research paper you'd like me to refine, and I'll be happy to assist you in creating a concise, technically accurate summary for voiceover narration. The generalized implicit follow-the-regularized-leader algorithm is discussed, providing update rules for common losses such as the hinge loss, absolute loss, and squared loss. This is followed by the proof of corollary 4.3, establishing a regret guarantee through two upper bounds on the cumulative sum of gamma t values. The first bound is derived from the definition of gamma t, while the second utilizes the properties of the gradient norm and the choice of lambda t. Combining these with the result of lemma 6.1, the final regret guarantee is obtained. The section concludes with the proof of corollary 6.2, involving the computation of the proximal operator for the surrogate loss function LT, crucial for understanding parameter updates based on the current state and gradient information. The generalized implicit follow-the-regularized-leader (FTRL) algorithm is a variation of the classical FTRL algorithm, offering flexibility in online learning and optimization. The update rule for the iterate xt plus 1 can be expressed in two equivalent forms, derived from equations 6 and 7. The first form involves the regularization term LT, xt, and the gradient gt, scaled by the learning rate lambda t, ensuring the iterate remains within a feasible region. The second form highlights the role of lambda t and LT, xt, in shaping xt plus 1, demonstrating the algorithm's adaptability to different problem settings and regularization schemes. The equivalence of these update rules is a result of a careful analysis of the optimization problem, leveraging the properties of LT, xt, and gt. The resulting algorithm is well suited for a broad range of applications, including online convex optimization and machine learning. The presentation of the two equivalent update rules provides a clear and concise summary of the key ideas underlying the generalized implicit FTRL algorithm. The algorithm's flexibility allows it to adapt to various problem settings and regularization schemes, making it a powerful tool for online learning and optimization. The author's use of precise mathematical notation and careful derivations ensures that the algorithm is rigorously defined and easily implemented, providing a valuable contribution to the field of online learning and optimization.